Bonjour, merci Stéphane pour l'invitation. Je vais parler en anglais. J'espère que ça va aller pour tout le monde. Si vous avez des questions, vous pouvez les poser en français. So I will talk in English, and I will have this seminar or lecture on weakly supervised learning for visual recognition. So it is, I'm going to talk about sort of the current state of the art in visual recognition, and so what I believe are some of the key open challenges. So you will see what are the current research problems and some of our recent work in this area. So first of all, just to set the domain, so the research domain is computer vision, which is really about extracting information from images. Our human visual brain is amazing at this task, it's very good at this. So we can easily, when we see an image like this, we can understand immediately what is going on in the image, what has happened and what may happen in this image. We understand what are the individual objects, people, their relations. For computer, this is still very hard and it's still an open research challenge to achieve a similar level of visual competence as the human brain does have. Just to illustrate that, what really the computer sees is a matrix of numbers as the input. So this is just to set the stage. More on the research side, one of the reasons I'm really excited about computer vision and visual recognition is this. So images and videos are all around us. Archives of visual information store internet videos, TV channels, or historical imagery. And cameras are all around us, from surveillance to car to personal cameras. And what I'm excited about is just thinking, wouldn't it be great if we could learn from all this visual data? What if we could automatically understand all these different data sources and devices? So just to give you a few examples of what this could mean, this understanding, why would it be great? For example, imagine that we could analyze surveillance data from all cameras across the entire city and extract statistics of human behaviors. For example, to improve road safety, urban planning, or commerce in the city. Another example, and I will talk more about this area, imagine that we could have a machine which could analyze instructional videos automatically and identify sequences of manipulation actions to achieve certain tasks. And to build machines which could autonomously perceive, reason, and act on the environment. For example, to operate in dangerous environments or help people to achieve complex tasks. Another area, and I will talk about this a bit more in detail, is what if we could sort of learn representations from this data which would generalize to different conditions, and we could have machines which could localize and navigate themselves in complex, changing visual world. And just to give you an example, in autonomous driving, we would like to have vehicles which can navigate themselves across different conditions, even if it's day or night, or winter, or summer. And this is still a challenge, and I will talk a bit more about this. Or if we have a robot which will navigate in indoor environments. So this is the same room at the different times of the day, and you can see it looks very different. There are people, these blinds are closed. So we would like the machines to really cope with these kind of changing environments. So computer vision as an area is not new. It has been around since the 60s at least, and it has had some great successes. And these are a few examples. Your car license plate is read on highways. You may not even know about this. Cameras run face detectors to localize faces, adjust the setting of the camera. There is even in manufacturing, there are sort of vision used to guide robots in constrained setups. Or your phone is running computer vision algorithms, for example, to do visual search. So there's been great successes, and in this course I probably don't have to sort of spend too much on this, but we've had in the last sort of past 5 or 6 years, we really had a significant progress in the performance of visual recognition algorithms, largely due to the kind of coming back of convolutional networks at a large scale. And this is just a graph showing performance on one of the benchmarks in visual recognition. This is the ImageNet benchmark over the years, and this is the error rate on the y-axis decreasing over the years. And you can see that sort of since about 2012-13, the sort of deep learning and deep convolutional networks have significantly reduced the error rates on this benchmark. And it has been like that and across many different tasks. So just to give you an example of what a current state-of-the-art visual recognition algorithm can do. So this is an object detector called YOLO, published 2017. And I'm hoping the sound is not going to be very loud here. Let's see. Can you cut off the sound, please? I would like to talk about it. So you can see it's really, so these bounding boxes are different object detections overlaid over the video, and this thing is running live. Could you please put the sound even down? So there is a predefined set of objects which have been pre-trained. So object detector has been pre-trained for a predefined set of objects which include people, motorbikes. And on the first sight, it looks really impressive. So we can really detect and localize all these objects in this fairly fast-paced video. So this is one example of a frame. I just stopped the movie in one frame and showing you the individual detections which were output by this detector. And you can see it's really detecting, here are the different people. There is an umbrella, which happens to be one of the objects in the data set used to train this object detector. But you can see that some people are not detected. For example, the person here or the person here. Some objects are not detected at all, like these things here. There's some sort of stuff with material, or there may be a card in the background. So it's working reasonably well, but there are still quite a few mistakes what a human vision system would do. And you can see these are individual people detections. It doesn't say what the person is doing and doesn't really understand what was happening in the whole movie. There was a chase happening. Someone was chasing someone else. So this is an example of a recent object detector. And here we're coming back to the first image, which I was showing at the beginning. And this is running this is an algorithm doing captioning of an image with natural language. You will have, I think, a lecture-specific seminar on natural language next week. But this is an example of a joint, and I will show more, of joint models of visual information and natural language, where the algorithm can produce bounding boxes and short sentence fragments. And this is applying the same algorithm on the first image. So you can see the output. It says, well, there are some people walking on a sidewalk. There is a large building in the back. Maybe the building has many windows. Yet it doesn't really understand or comprehend the whole story of this image. So still understanding the relations between so understanding the relationships between the scene entities, their actions, and the interactions is still a hard research problem, open. So after this introduction, what I will do for the rest of the talk, I will talk about three, which I believe are one of the key scientific questions open in the domain of visual recognition at the moment. And I will give you a some examples of our current work in the area at the moment. So the first one is, what is the right vocabulary of visual patterns? So here, and this is again going back a little bit to the history, how do we design a visual representation? So initially, at the beginnings of computer vision, people thought, well, we are just going to write down rules, how an object appears. So we are going to take a chair and we're going to describe that the chair appearance by listing the different the rules how the chair should appear. It turned out that this is very difficult. So describing this way chair appearance is difficult. So instead, what has really sort of turned out to be successful is use machine learning techniques to capture, to show, sort of collect a number of examples what a chair may look like, and then train a classifier to say what the chair is or not. And the classifier should learn automatically from these examples what the chair looks like, what are the important features. So this is summarized here, and it's really one of the successes of current computer vision and machine learning. It's called supervised machine learning. And again, you probably have seen a lot of this in this course and even before. So just a picture summarization. So what we do, we collect positive examples. And I will try to use this. We collect positive examples of chairs, then we collect negative examples of images of not chairs, so there will be other things. So this is training data. So we need these three ingredients. We need training data. We'll need an image classifier. So this is going to be a function f, which given an input image, will output a +1 if it contains a chair, or -1 if it doesn't. And then we'll need a training procedure. So this function f is going to have some parameters. And again, you probably know, given this class or course, what these parameters will look like, what the form of the function will be. And we will try to optimize these parameters on the training data to minimize the number of errors. So we'll have this is the loss on the training data. So just to introduce the notation, we'll have the function f, which given an input image will produce a score, and we'll compare the score with the label y. We have input images, labels y. And we will minimize loss function between the ground truth label y and the output of the function f over some set of training examples. So this sum is running over the number of training examples we've collected here for the task. I'm sort of using this because I will be extending this notation. So I just want everyone to understand this is the problem setup. We will often have regularization on the function f. I will not talk about this. So we may have seen some of this in this class, but I will not talk about regularization, which constrains the functions f. So in practice, if you want to do this, you need to collect millions of training examples. We will have classifiers with millions of parameters, and we will need powerful training hardware. And even on this, the training will take days or weeks. And so what I want to focus in the rest of the talk today, I really want to focus on the first part. How do we deal with the training data? And do we really need the full supervision for this task? And you may already see that, collecting millions of training data, it will not be an easy task. So you'll probably see that. And I will discuss two key limitations of this approach with respect to the training data. So the first one, it would seem that if we really want to detect all the objects around us, do we really need to annotate the full world? Do we need to annotate everything if we want to recognize it? And so it has problems. The first problem, it is expensive. So this is an example of an image where every single chair has been annotated. This is an image from some of the current object recognition data sets. So it's expensive, it takes a lot of time, but it's also ambiguous. How would you annotate this object? Some of you may say, well, it's a table. Some other people may say, well, this is actually a bench. Or is it a desk? Or is it a dining table? So even if you decide to annotate, it's ambiguous. There is different people may come up with different annotations. So that's problem number one, expensive, ambiguous. And second, which is, I believe, even more problematic, is the granularity of the visual representation. Sometimes you can't annotate even if you want to. So, and the problem is that the visual vocabulary, the annotation labels, is very large, a priori unknown before you want to consider a certain task, and it depends on the task which you want to achieve. It's task dependent. And just to give you an example, going back to instructional videos, what is the set of manipulation actions which you can do with a particular tool? How would you annotate that? And here, going back to surveillance videos, what is the set of human behaviors which correlate with pedestrian accidents? Again, how would you go and annotate that? So we need something else than this if you want to consider these difficult tasks. And one of the solutions, or possible solutions, is to have machines which would learn without human supervision, without the need for manual labels. And so this is a very active area of research at the moment. Many people are working on different aspects of this problem. One area is unsupervised learning. Well, what if we have just the images? Can we learn visual representations just from this data? Another one is weakly supervised learning. Then when you have the visual data, but you have all available metadata. Visual data does not very often lie by its own. It's usually surrounded by some other metadata, which could be, imagine on the internet you have an image or video which is surrounded by, it's embedded in some web page. So the YouTube videos may have tags, for example, or Street View images may have geolocation information. So weakly supervised learning is an area which tries to exploit all the available metadata for learning. And this is the area which I'll talk most about today. And that's where we in our lab have done a lot of work. And there is another area which is kind of coming to visual recognition now, or coming more in focus, and this is really learning by interaction with the environment. So if you have an agent which can actually act on the environment in some way, maybe think about a robot which can has hands, performs certain tasks, or moves around. So it can learn by interacting with the environment and getting feedback from the environment. So this is related to reinforcement learning, or may imitate, for example, people. And I will also talk about this, how to perform something. So this is learning by interaction. So I will focus on weakly supervised learning for the rest of the talk, with a little bit of kind of hints towards maybe learning from interaction with the environment. So the talk will be filled with examples of the recent work. I will not give much detail, kind of really technical details of these algorithms. It will be more like an overview on a high level. I'm very happy to talk about details of any of this work if you want to come after the talk. But I will try to highlight some of the key technical aspects. So I will show a bit of equations and highlight some of this, but not in too much detail, and show a lot of results. So we've done quite a lot of work on learning from instructional videos. I think this is a really exciting area, and it's exciting data. Now imagine that you are sort of on some abandoned route and you get suddenly flat tire. You do have internet, so you have a reception on your phone. So you can say, well, how do I change the car tire myself? I have a spare in my car, so you can Google up how do I change car tire, and then on YouTube you will get all these videos where people are showing how to do it and talking about it. So it's narrated. with different, so if you don't like the one particular one, there are other videos with different car types doing the same thing. So you can sort of see more examples. And this domain is actually quite big, and there are many different instructional videos online for different areas like cooking, gardening, or even healthcare. So there are millions of these videos online where people show how to perform a task and talk about it. So it's a combination of visual information related to manipulating objects, achieving something. And it's combined with a narration, so it's sort of a natural language. People talk about it. So very exciting data. And so in this research project, what we would like to do is to learn from this data. And for example, to learn some kind of a representation, which you can think of sort of an instructional manual, which we learn automatically from this data. I'm showing sort of one for IKEA. And why? Well, because you can then perhaps sort of upload it to the robot, which can do a task in a different environment, or give instructions via some augmented reality device to a person who doesn't know how to do it, to perform the task in a new environment. So this is an example of the data, and it's weakly supervised because, as you've seen in these examples, there was no object bounding box annotations. There was just a video input together with the narration. So we didn't know what parts of the text corresponds to exactly which object. And so the formulation which we will use for the weakly supervised problem is kind of extending, or we can think of extending the basic supervised learning formulation, problem formulation. So here we have a set of inputs xi and supervisory metadata yi. So this is not output labels, this is the metadata here. And we want to learn a mapping f from the image space xi to some kind of a learned or hidden or latent vocabulary z. So in this case, we have again discriminative loss on the data, regularization, and we want to minimize this loss not only over the f, the parameters of that mapping, but also to identify or to over the vocabulary z. So we want to learn both the mapping and the right visual vocabulary. So this problem would be under constraint as it is because we're optimizing over both f and z. So to regularize it, we need some additional information. We need the constraints. And they are coming into the problem formulation in the form of sort of constraints between the metadata y, so this is the input, and the vocabulary label z. So it's written here as a simple linear constraint, but it can be more complex. This is just a simplified example. So just a high-level summary, very similar to standard supervised learning, but the supervision is not entering directly the loss function as before, but it's entering the problem in the form of constraints on the output space. So you will see several different examples. So this is the key idea. You will see several different examples of this idea appearing in the rest of the talk, where we use the supervision is coming in the form of constraints in the problem. So coming back to instructional videos, so this is one concrete example of work where we do this. So the input is a set of videos with the narration. Here it's in the form of natural language, so direct transcript of what people talk about. So are different videos, and what we would like to output in this case is the sequence of the main steps. So this would be, for example, loosen the nuts, jack up the car, remove the flat tire in order to achieve the task. We also like to have a visual and linguistic representation of the step so that we can recognize if we see that step in a different video, maybe from a slightly different viewpoint. And we would like to temporally localize these different steps in the video. So here these are different colors for the different steps. Yellow is loosening the nuts, and this is here temporal localization of that step in the video. It's both the language and the video. So that is desired output. The problem is difficult because there is a very high variation in natural language. I think Piotr Bojanovský will talk about it next week, I'm sure. You can express the same concept or same idea in different words. So these two sentences refer to the same concept. Start by loosening each bolt or first undo the nuts, but you see very different sentences. Similar in the visual domain, you can perform the same action, which is really loosening the nuts on the wheel, in two very different ways. So this person using hands to do the task, and this person is using the foot. So it's both the visual and language problems are very difficult. Here, what we take advantage is the complementarity of this information, that in some cases we will use language, some cases we'll use the visual information, and together these two modalities help us to address or solve the problem. So here, I will not talk about this in detail, but given the language narrations, we extract the sequence of the main steps. Here again, they are in colors. And then we use these steps as constraints for the problem. So here we have the video. We know that the step occurs in the narration, but the narration is not directly aligned with the video. There is a temporal uncertainty. If someone talks about it, he may do it sometime in the video around that, the point he talks about it, but not exactly the same at the right moment. So we use these, the language, the narration, as a constraint in the problem, and how to help to localize the action. So how is this formulated? Again, the basic idea is that we have a latent variable, z, which runs along the video and and it's sort of 0 in the places where there is no action, and 1 when there is a particular action happening in the video. And then from the narration, from the text, we know that jacking up the car occurs in a certain temporal interval in the video, but we don't know exactly where. And we convert this information in the form of constraint on the latent variable z. So we know it should appear somewhere here, don't know exactly where. Then we have the latent variable saying action appears or not in the video. We want it to be 1 where the action occurs. So you can see here we would ideally like to be 1 at the moment where the action occurs of jacking up the car, and 0 everywhere else. And we have the information we have from the metadata, it occurs in this interval. So how would you convert this information? It converts somewhere here in the form of constraint on z. So one possible way is that you say, well, the sum of these variables of z in this interval has to be equal to 1. So it's a very simple linear constraint that, or if you can have multiple actions, the sum of these variables of z in the time interval has to be greater than 1. So it's a simple linear equality or inequality constraint. And in this way, you can incorporate the supervision from the metadata in the problem formulation. There are other ways of doing it. One can use also max, for example, that you want the max in this area to be 1. And this is used in other sort of problem formulation which we used with neural networks, but I will not talk about this in detail now. The main key idea that we can convert this information from metadata into a constraint. So this is the overall formulation. Again, the loss, a regularizer, loss on the data, on the training data, regularizer. But what we want to minimize over the parameters of the here function f, it's slightly different notation, they are expressed as w. But the key important thing is that we have constraints over the latent variable z, and this incorporates the supervision from metadata which we have. Here it's linear inequality constraints. So here are some qualitative results of, so this is loosening the nuts, and you can see video segments, clips, which demonstrate or show this, this action from using different tools, different viewpoints, and similar Here is jacking up the car and removing the wheel. And this is an example of an output where this is the set of steps automatically recovered from the video, and these are this is the ground truth the intervals, and these are the locations of the actions where the algorithm thinks this is happening. So, for example, here it will recognize that the person is checking up the car. So this is an example result. We have much more of these on this web page for also different tasks like making coffee. So what you've seen now is, so we've looked at this question of how do we define the vocabulary of patterns, and we looked at this, so it's difficult to do fully manually in some situations, so we would like to use other forms of learning, like weakly supervised learning from available metadata. The second important, I think, scientific questions we have in visual recognition is about the generalization. And I'll spend some time on this one. So the key question is, how do we generalize to new conditions and situations? I think this is very important if you want to really have machines which will walk around the environment. They will see new things which they haven't seen at training, eventually. So the issue is, so we have a large variation due to viewpoints, scale, illumination, and occlusions. For example, as you saw, there are two very different ways to perform the same action. Or how do we recognize the same action, someone riding a bicycle, from very different viewpoints? So it's a huge amount of image variation. And so coming back to the formulation, the key question is, what is the appropriate form of that mapping fx? And probably most of you, and so that we can capture the image variation and also learn it from few training examples. So probably most of you would know the answer at the moment, that what we really use very successfully is our convolutional networks as the mapping fx. And it can capture a large amount of variation, but the learning, we still need quite a lot of training data to learn them. So these are just a few, second recap. Given an input image, these are sort of layered representations, having a sequence of nested layers which output a representation Z, just to, again, have the notation, have been around for a long time. Recently, seen a lot of success in visual recognition. And important that each layer has these learnable parameters. Here is a linear operation. So Stéphane was just talking about this. Linear parameters, here W and B. And of course, in computer vision, this is a convolution. So it's not any linear operation, it is a convolution, which is very successful. But what's interesting, and you may have not in this class seen, is that these learned parameters for each layer, they turn out to be transferable across tasks. So this turns out to be a very important property, which we didn't quite have before in visual recognition, that we would have this transferable representation. What it means that we can learn that representation on one task when you have lots of examples, and then transfer it to another task where there is maybe not so many examples. Of course, there is at the moment very little theoretical understanding how this works exactly, but empirically works quite well, and there is happening work on the theoretical side as well to explain this phenomena. So experimentally, we've shown data around 2013-14 together with several other labs at the same time, sort of discovered or found this or quantified this property in visual recognition. In other domains, it's been known even before. In audio processing, for example. The other downside a bit, this representation is excellent for 2D images. If you want to do video or 3D objects, it's still a bit difficult. Or we don't know what is the right representation for video. We have some, but it's not clear whether we can just directly take what we have for images and apply it for video. There's a lot of research happening on how we represent video and 3D information as well. The convolution itself doesn't quite scale up to 3D, and possibly it's a computational issue because the 3D sort of voxel grid is much bigger, but at the moment it's still an open research question. I will first show you an example of success in a 2D image and then show you some of the recent work which we are doing in the area of video and a little bit of 3D as well. So convolutional neural networks are very successful. You may have seen this image before. That was one of the first examples which we were very impressed by around 2013. So the CNN detects there is a bus, but also, and you can try this yourself, is there a person in the image? Some of you may have seen this. So who sees a person? Some of you I see a person, some of you don't. There is a person in the image, in fact. It's hidden here into the corner, sort of next to the bus. And that was an example where we didn't see the person. We thought it's a false positive, but the network has clearly localized and found the person in here. So we thought, wow, this is impressive. So there is something happening interesting here. And this is another example of output of a convolutional network. This is a fairly complex scene with multiple objects, and these are output probability maps, which the blue shows low probability and red colors show high probability for different objects, like a chair, dining table in the middle, person, potted plant. This happens to be one of the objects in the database. You can see there are sort of two high-scoring blobs here, and there is one here, another one here. So this is just an example. For 2D images, been a lot of success, even commercially. So some of our students have done startups in this area, trying to do different recognition tasks. And this is an area which does see a lot of applications. What I will show you is another sort of research work in this area, which is sort of joint work with Ivan Laptev and our student Antoine Miech, which is in the area of video recognition, and it's looking at learning joint representations of video and language and text. And it also touches on the area of generalization. We want representations which generalize to new situations. So here the goal is, given an input video like this one, you would like to produce a caption, a natural language sentence, like two girls eating a sandwich. And we would like to also address the reverse task, which is retrieval. Given a sentence or short language fragment, eating a sandwich, we would like to find this video in a large corpus of videos. Imagine you have a database of video, like a stock footage, and you want to query eating a sandwich, and you would like to find that video. So these are the two tasks which we are looking at. And I think the real challenge in this problem lies in generalization. So as I've seen, we'd like to have representations that generalize. And in this case, it's one example of this is to new objects and situations. So in training, you may see video. So we'll train this representation from a corpus of videos and language sentences. So it will see caption that are eating a sandwich, you'll see at training. And then maybe we will never see a video of someone eating a banana. But we may have a still image which is captioned a yellow banana. So we would like then combine this type of information, action, eating, plus a new object, and then be able to generalize to a new situation. An example is this one. Example is this video, where given someone eats a banana, we would like to recognize this new situation, even though we've never seen someone eating a banana here. This is a particular way of eating a banana, which you may not want to try yourself, but I hope you get the idea of the generalization of, in this case, to new combinations of objects and actions. And I believe in sort of language video understanding, this is one of the fundamental issues, even in actions, because it's unlikely we will ever see all possible combinations of actions and objects at training. It's combinatorial. We are unlikely to collect enough training examples. So another example is audio, and hopefully here, if I can get a bit of audio so you can hear. Well, imagine there is an audio of a dog barking, and which may be captioned with dog barking, and then we have a still image of dog lying down. Again, we would like to combine this information, have a model which can combine this information, which sees audio of barking and still image of dog. And then, given a new query, like here, so this dog is barking here, if we don't have the audio here. But given a video where a dog is barking, we can caption it, a dog is barking. Or given a sentence, barking dog, we can find this video. Again, you can see the generalization. At training time, we see separate audio, a still image, and at test time, we would like to combine this information and generalize to a new situation where we see those two together. So I wouldn't say that we've solved this problem. I think it's one of the actual fundamental problems in visual recognition with natural language as well. But we have made step, I think, in this direction, and we've designed a convolutional neural network architecture which addresses, which sort of makes a step in this direction. So we have, input, we combine multiple different sort of modalities, if you wish. So we have, so this is different branches. This is the input, appearance. You can have motion descriptors, face descriptors, if you want to say caption, emotions, and audio descriptions. And they, each of them have a separate small convolutional network, a branch in this architecture where there are some descriptors extracted from individual frames of the video. They are aggregated over time into a single representation, which is then transformed. So this is a special, it's called gating embedding unit, which we've invented, which computes, given this information, a continuous embedding vector. And all of these these embedding vectors are then combined with the text information. So again, given an input text sentence, we again have some aggregation over the sentence and embed the sentence into different vectors depending on the different modalities. So there will be this same sentence will have a different representation to combine with appearance to compute similarity, and we compute similarity between these two vectors using a simple dot product. And we have a different embedding space for motion and for face descriptors and for audio. So just, actually I have one slide just to, so the particular details of that representation are in this paper, and it's a representation which we used for video, which we used, so Antoine has won the YouTube 8 Million Video Classification Challenge 2017 with this. So it's a powerful representation for video, so we use it in this architecture here. So what we have now, we have these different branches which have combined appearance, motion, face representation together into a final similarity score, which computes given a sentence, so input is a sentence, and a video of these different representation, output is a similarity, how are similar these two. So what you can see is that this is a weighted combination, and what's interesting that we estimate these weights from the text sentence. So this is a combination, so we have these individual similarities combined with these expert weights. We call this model mixture of embedding experts, and these weights are depending on the output-input sentence. The intuition is that if you have a sentence where man is practicing karate, the network can estimate the weight and give more weight, say, to motion descriptors. Or if it's, say, Obama is speaking, it can give more weight to face descriptors. And these weights are learned on the training data. I will just show you some examples. So we run experiments on 2 different data sets. At training, the network sees examples of videos and natural language sentences. This model does very well on the benchmark. It's, I think, one of the best, if not the best, I think. It was best when we sort of wrote the paper on that benchmark. And I'll just show you a few examples. So that we have actually online a search engine where you can search this database of 100,000 videos. You can make a query like people dancing, and what you're gonna get is a video like this. These are clips from movies. You may recognize some of these movies. If you put people dancing in a nightclub, you will get a different video, which is so you can see that depending on the query, you get a different return. You find a different video. Here is a running in the city. So this is if you search the database for running in a city, if you search database running in a forest, you will get a different video as the top track. So you can see that we combine this information from video and language together to have a representation where you can put a new query, which is a combination of different words, and you will get back, you will query the database using these continuous embedding vectors, measuring the dot product as a similarity, and get the results back like this. There is a website. You can actually try this yourself. It's not perfect, but I think it's an interesting demo. You can try and see the current, what works and what doesn't in this domain. We also have done some work on looking at sort of structured, more structured representation. So here it's only like a single embedding for the whole sentence, but we're also working on having representations explicitly try to distinguish relations, like in a subject, object, and a relation, and generalize to new relations. So when you have person, you see at training, you see person riding a horse, you see a dog, and maybe person riding a bicycle. But given this information, you would like to recognize completely new relations which you haven't seen before, like person riding a dog or a dog riding a bicycle. So this is a more structured representation which allows you to do these combinations which you have not seen at training and recognize them at test time. Again, this is not perfect. This is kind of a work in progress, but I think it's one of the very interesting research problems, how to do this. We can do this very well as humans. Can we have machines which will be able to recognize these completely new, unseen things? This problem of generalization, I think, is across the domain of visual recognition. As I was showing this example of localization in changing conditions, it's practically a very important problem because if you have current cars, they rely on accurate localization on the road. They have a 3D model as a map, which is accurate, and they need to drive well. They need to localize themselves with a precision of 20 centimeters. And this localization is based on combining different information, lasers, sort of LiDARs, and visual localization. Problem with visual localization, and we've tried that, we have a whole benchmark on this, is that it doesn't work across changing conditions. So at the moment, if you had a car, you wouldn't be able to drive it at night. So there is, I think, a very nice research direction. How can we make these representations to generalize to new conditions and situations? We've done a bit of work on that, learning from Street View data. This is a nice combination of generalization and weak supervision. There is a Street View time machine where you have the same scene at different seasons or different times of the year and different years, in fact. And we've learned a representation for visual localization from this data. It's weakly supervised because the geotags are approximate. They are not super accurate. So we have to do additional work to sort of convert this information into a suitable, this metadata into suitable supervision. So we have special algorithms to do that, which are similar to what you've seen before. They are kind of acting as constraints on the learning problem. And these are some examples, difficult even for people, I think, but this is a query, and this is the same place recognized as the same location across different viewpoints and illumination conditions. You can recognize yourself. It's not easy, but it's possible now automatically with actually reasonable accuracy. And coming back to the indoor localization, this is an example of also very recent work on given an input image, maybe coming from a robot, localize itself in a big environment, like a university campus. Very difficult because all the corridors look similar in the campus, yet sort of we made some progress on this, again, the changing environment is changing, that's why it's difficult. We have a data set which captures this type of variation, so we can evaluate progress on this. This is just an example. This is how accurately localized distance in meters. This is a % of correctly localized queries. So this is sort of previous state of the art in this problem, and this is sort of algorithm based on convolutional networks, and it really works much better than what there was before. It's still not perfect. There is still a long way to go. And so I think I have sort of 5 or so minutes left. So I will show you a little bit on this last problem, which I think is very challenging, and it's sort of beginning to be work in this area. And it's more about how do we reason about visual data, how do we interpret it. So it's sort of going one step sort of further. We've recognized entities from weak supervision, maybe their relations, but can we do sort of additional reasoning on this data? Now, what do we even mean by doing reasoning on visual data? So I think these are interesting research questions. I will show you sort of 2 examples of work very quickly, and it's about more reasoning about actions and objects. I think it's an interesting area, practically important. If you want to manipulate objects, you need to understand the relations between how the manipulation actions and how it changes the objects, possibly. So this is an example of how actions change states of objects. So you have a pouring action here can change the state of the cup from being empty to being full. So when you pour the coffee, and this is actually happens many times where an action is changing the state of objects. When you open a door from close to open, fill a water bottle or cut bread. So this happens often, and here we build a system which can recognize that. In fact, can learn automatically without, so in this weakly supervised manner, can learn what are the different states of an object and what is the manipulation actions where they happen in the video. We equip, it's not completely sort of unsupervised, we equip the system with an object detector. So it has a generic cup detector, but doesn't know empty or full, but yet can learn this from data. Problem formulation, I will not go into details, but again, it's building on what we had before. So it's a cost function for actions, cost function for objects, and what we have on top of it to model the relations of objects and actions. To reason about them together, we have an additional terms which model their relations. At the moment, we design them by hand to some extent, how we want to model the relations. Eventually, we would like to learn all of this from data as well. We would like to learn what are the typical relations between objects and actions. At the moment, it's more hand design. It's a very interesting research problem how to learn this from data as well. Here are some examples of, this is empty cup, it's a pouring coffee action, empty cup, pouring action, and full cup. And you can see the different objects, the different sort of variations of viewpoints. And it's sort of automatically learn empty cup, if you wish, recognizer, a full cup recognizer, and then the pouring action. Here is another example of instructional videos where there is a wheel of the car, there is the putting wheel action, and there is a on the car wheel. Or the instruction videos for many different tasks. This is opening oysters. So this is, again, the system has recognized there is a closed oyster, there is an opening action, and there is an open oyster. At the moment, it's sort of more building models of appearance, how a closed oyster or open oyster looks like. It doesn't know about the physics of the opening at all. It sort of can recognize if it's closed or open. Even that could be very interesting information, because if you can recognize if it's open or closed, you can put that perhaps as a reward signal into an algorithm which will try to open it, maybe a robot, and will recognize if it's open or closed. At the moment, a lot of the reinforcement learning have engineered rewards. Here we are trying to essentially learn a reward function, if you wish, if you know more about this area. And so what I will finish is sort of another piece of work which also goes into this direction of reasoning about objects and actions together. It's a very recent work with a number of colleagues combining expertise from computer vision recognition and robotics. And here the goal is given an input video of someone doing a particular task which involves an action of a tool, like here the hammer, the sledgehammer. So this is the input, single YouTube, so this is a clip from a YouTube video, someone showing how to do this. And output is a 3D interpretation of the action. You can see these are sort of joints of the person. There is a tool modeled, and the yellow arrows, if you see maybe from the back, are the estimated forces of this interaction. So we have a sort of physical dynamics models which, given that video, we try to estimate all of this, and we modeled also the contacts between the person and the tool. So this is kind of a combining expertise from visual recognition with constraints, physical constraints. And so maybe I'll just give you a very high-level overview. Input is a video. We have a recognition stage where we recognize 2D human pose in the image. We recognize contacts, whether a particular joint is in contact or not. Green is in contact with the ground. The green joints are contacted with the tool. The red joints are not in contact. We have an object, 2D key points, again, sort of learned object detector. So this is recognition stage, all in 2D, and we then combine this 2D information in a consistent 3D interpretation of the scene, which involves modeling the interaction between the object and the tool, including forces. And eventually, we would like to transfer this information on a robot. We haven't quite done that part fully yet. We have some initial result, but not fully yet. But that's the hope, going all the way from single input video to performing the same action involving interaction with an object on a robot. And maybe sort of, this is an example of a input video. So this is the output of the recognition stage. This is the recognizing the 2D joints and on the person and the object. There is some interesting innovation we've done in how this is achieved. I will not talk about this, but instead, given the timing, I will go to just show you the results of the estimation stage. It is really formulated as an optimization problem where we want to sort of minimize an objective which the 3D model is reprojected into the image. This is kind of reproducing what the video is showing. But optimizing over the 3D. So the parameters we optimize over are the configuration of the skeleton, the object, and the contacts and the forces as well. But we have all these constraints on the problem, and that's the additional supervision we give to the problem. We know there is a physics, there is dynamics sort of happening, and modeling the tool has to be in the contact between with the person to achieve the task. And all of this acts as essentially constraints on minimization. At the moment, these are two separate stages, but one can envision doing all of this together, that these constraints, physical constraints, will act as constraints on a learning problem. Here we kind of do these separately. And here is an example of output qualitative results given input image. These are output, the same scene, the 3D representation with the object from two different viewpoints. So this is, again, generalization across viewpoint because we have a 3D model now with forces, so we can really sort of see how the action would look from different viewpoints. And I will kind of finish here with showing you some examples of these manipulations. This is the input video. This is our result. Again, the yellow arrows are estimated forces. There is the tool which is in contact with the hands of the person, which we model here physically and recognize it from the video. And this is output of a baseline model, which is recently published, which does not have all these dynamics constraints or contacts, or does not model the tool. So you can see it's much more noisy and sort of, well, doesn't have the tool, and some of these interpretations are just not plausible. Another example, again, input video, our result, and then the baseline. We have different tools. Think these are, we have at the moment a relatively small vocabulary of tools, but the next challenge would be scaled it up to many examples, many tools, and possibly sort of, as I said, connect the constraints from physics with the learning so that we can really use that as additional constraints on the learning problem. This is really, will conclude. So what you've seen is some of the state-of-the-art quick overview, and then some of our, what I believe are key, sort of some of the key open research problems and some of our work in the direction. It was learning vocabulary from data, how we set it up as a weekly supervised, to learning without requiring manual supervision, very important, I think, research problem, which has lots of work. We need representations that generalize to different situations and conditions, because if you want to have machines which go around real environments, they will see new situations and new conditions. And finally, we want machines which will be able to reason about the visual world, similar as we do as humans. So what I think we will see many more applications in years to come in constraint setups. But if you want to really long term, we want to have machines which can do sort of autonomous learning, reasoning, and interaction with the physical world based on visual and other inputs. And I think this will require like collaboration with other research domains. Robotics, natural language processing, speech, of course machine learning, but also control, for example. But it's a very exciting area and time to be in, I think, at the moment. So that's all from me. Thank you very much for your attention. Thank you.